Awesome. All right. Well, thanks for the intro. And yeah, I'm going to be talking about the edge of tomorrow, dark forests, relativistic computing, and how to power a new internet. Or I figured, this is the first talk, and each section had a little blurb. So I figured, yeah, I'll give the 10,000-foot view, and hopefully tee a bunch of other people up to talk about things. So this was the question, and really the main factors here are, where's the line between all this Web3 stuff and decentralized computation and traditional systems? How do we choose which way these things go? So my name is Zelenka. You can find me anywhere on the internet as Xpeed. I'm the co-founder and CTO at a company called Fission, and we're working on infrastructure and SDKs for edge apps. My background's mostly in programming language theory, virtual machines and distributed systems, and I've done a bunch of standard stuff. If you're interested in any of that stuff, talk to me later. I have 10 minutes. I'm going to keep blowing through this. So basically, this is the picture today. About a third of the internet is run by just AWS, and AWS, Azure, and Google essentially are the current hegemony, if you want to put it that way. And the overall trend is that this gray segment, this other, is shrinking. And I don't know about you, but I don't want them to own the entire future of the internet, right? Yeah. So essentially, what we're doing in Web3 is nothing less than connecting all of the world's users and services. We're essentially creating an HTTP for storage and compute, open, interoperable, and everywhere. And for this to work, it has to be substantially better than Web 2, right? We can't say it's like Web 2 but decentralized. Who cares, right? It has to actually be better. So let's start with consensus, something a lot of us here will know a few things about. And there's trade-offs to having consistency, and how much consistency and consistency across large number of machines, right? So global distributed consensus is really expensive. I don't mean in cost for submitting a transaction, but actually in time and latency, right? This is a hard physical limit. We cannot do better than the speed of light, period, right? Years ago, I had a CEO tell me to make it go faster. I was like, no, you don't understand. It's not physically not possible. It's still really useful for a lot of things, right? Like mutable pointers, public commitments, broadcast distribution, all of this stuff, right? But not for absolutely everything. So where's the line? What's the landscape look like? So we have commons networks, far edge, and cloud and traditional edge, and lots of different projects all in here. And we need to find ways to interconnect them in a way that is interoperable and that works out of the box without people having to do a ton of work, right? These should be open, extensible protocols. We should have all of our IPFS stuff working together. We should have the ability to move from Polygon to your iOS to WebAssembly into traditional Kubernetes and back. So we have this growing toolbox. It used to be that you had client and server, 15, 20 years ago, and now we have serverless and P2P and local first and offline stuff and networked data and blockchains, right? This is a lot of things that we have to get to work together. So why do we even care about having all these different parts? As I mentioned before, a lot of this comes down to light speed. This is a graph from Ericsson. They're a big hardware networking provider. And they're showing, for a lot of use cases, things that we really care about, like smart grid and automated vehicles, we need to be sort of in this 10 to 100 millisecond range for the complete transaction, the whole thing, right? You literally can't do that with a blockchain. The distances are too big, and then you have to achieve consensus after that. Not possible, right? So there's a bunch of stuff under this line where we need to go to edge or directly on device. No other option. So let's take 8 milliseconds. This is usually the cutoff. It's 40 milliseconds for edge, 8 milliseconds for really real-time stuff. What does that even look like? Well, if we take it as the speed of light in a vacuum, this is about the distance for one way. If we do a round trip, it's about that. And if we put this in fiber, because light actually travels slower in fiber or in copper, it's about this. And this is perfectly straight, not going around mountains, nothing else. Like in an ideal scenario, theoretical maximum distance. It's not very far, right? And that, yeah, immediately rules out this one. One way to think about this is that we live in these causal islands, right? This is actually physics, not computer science, where as you create new information, it ripples out to different places where it can have an effect. Some people like to put this as a light cone, where you're at the middle here, you're at this line, and as time progresses, these get wider. And you say, well, maybe I can just live in the part where it overlaps, but you are now trading off time for consistency, right? So you can absolutely do this part here, but it's slow. So we have a spectrum that we can work on, and it's completely fluid, right? You have it directly on device. You have now compute and storage going directly on 5G towers, so literally down the block, right? You have edge data centers, and then really, really far, you have cloud computing and blockchains. And of course, this is now also getting shorter with things like Starlink. So we have local first, real-time, state channels, caching, transactional processing, very close to users, relay, replication, consistency, and tasks. A little bit further out, we need a little bit more consistency, and then global consensus, aggregation, training, and analytical processing way in the data center or on-chain. So that gets us this from very fast, but less consistent, to very slow and very consistent or very heavy processing. One way of handling this, when you're working really fast, is to weaken locality and to take advantage of some nice structures that let you do computation and storage in little pieces and then bring them together later. But you're giving up this idea that there's a single system image, that there's one way to look at the data, right? You have to throw that out. So we have to throw this vision out, but then that also means that we want to secure our data. We have to secure our data literally everywhere, right? So we call this, part of the idea is the dark forest. I love this quote. Cryptography is a tool for turning lots of different problems into key management problems. And so we're going to lean into that one pretty hard. One approach to this is to assume that all the pipes are broken and make all of the data that's public private, and then put the private data in public places. You can still give people access to parts of the data by granting them keys that give them access to things below, and even sort of granular access within that, and sort of whichever part you like. And there are lots of ways of doing this. And there are also ways of, so that's read access. What if we want something like write access? Well, not only do we want it to work at all and to say that somebody has access to these things, but we want it to be able to share across multiple applications, multiple people, through multiple paths, and to not have to worry about which application that lives in, to have zero coordination between them out of the box. Traditionally, this has been done with OAuth, which requires a lot of coordination and lots of steps in between because it has to go through a single authorization server. But with Web3, we can substantially improve this picture, right? We can make it much smaller and much easier by using cool cryptography, basically. The way I think about this is that we are slowly wheeling in Web3 into the whole internet by making it more convenient. And finally, and I see the timer ticking down, decentralized compute. And this is stuff that's really picking up steam more recently. So yeah, we've been able to do compute off-chain and on-chain for a while. How do we blend the two? How do we get a single view? Well, we can take data and computation and put it into a single graph, run the computation, and then store the outputs. And this gives you a few benefits. One, you never have to run that computation again. You have it cached. And it's a consistent model across everywhere you'd like to run it. We're calling this code name IPVM, Interplanetary Virtual Machine, and IPLI, Interplanetary Linked Invocation, so that we can decide, do we want to run off-chain, on-chain, or in high parallel, anything like that, purely declaratively. And the nice thing, as I said before, is you can cache these and reuse the computation later and move them around, suspend them, ship it around, and resume. Wrap up. 2 seconds left. This is the stack diagram of what everybody needs to work on. Small. Thank you.